All right, we were talking about 9.6, which is the ratio and root tests. And these are the last tests that we're going to learn for convergence and divergence, which you're probably relieved. So we will be taking a quest over all these different tests to make sure we're good with that before we move on with the rest of the chapter. And so after this section, we will be reviewing and then doing that quest. All right, I say quest because it's a little bit bigger than a quiz. All right, so the ratio test. First, we have a series with a sub n as non-zero terms, and we say it converges absolutely if the limit as n approaches infinity of a sub n plus 1 over a sub n, and we're talking about the absolute value of that, if that is less than 1. And let's think about this for a minute. If you remember what we were talking about with our alternating series lesson, if this numerator and is smaller than this denominator, that's what will make this ratio less than 1. And didn't we say in alternating series that if the n plus 1 term is smaller than the n term, then it's going to be converging. So it's basically we're doing the absolute convergence test, and really that makes sense because if these values keep getting smaller and smaller, I'm adding smaller and smaller value, which means it converges. Okay, so alternately, if this numerator is larger than the denominator, so the nth plus 1 term is bigger than the nth term, then that ratio is going to be greater than 1, or we could say it's equal to infinity as well. So that means I'm going to keep adding larger and larger values, and it will not converge to a sum. So that's when it diverges. So we've talked about this intuitively before. So this is another test to show that that is happening with our series. Okay, and here's the last part. It's important. If that ratio is equal to 1, then the ratio test is inconclusive. You cannot use it. You need to use something else to see if that series is convergent or divergent. So this test is very, very useful in series that have factorials and exponentials. Okay, so let's look at an example. So notice in this series that we have exponentials here. So this would be a great one to use for the ratio test. Okay, and notice even though it is an alternating test, we're going to have a little bit harder problem with showing that first condition. So that's why this ratio test is very useful. Okay, so we're going to do the absolute value of this, remember. So we're really going to be testing our a sub n is going to be n cubed over 3n. Okay, so we're going to take the limit as n approaches infinity of a n plus 1 over a n. So let's look at a n plus 1. So all that means is I'm going to be doing the n plus 1 term. So that would be the limit as n approaches infinity of n plus 1 cubed over 3 to the n plus 1. Now I'm going to be dividing by just the original. So since this is already a fraction, I'm going to be multiplying by the reciprocal. So I'm going to be multiplying by 3 to the n over n cubed. And here's where we get to be creative with our algebraic manipulation. I always think this is fun. I know you guys may not. So I still have n plus 3, or n plus 1 to the third power. But I want to simplify this piece down here. So 3 to the n plus 1 is the same thing as doing 3 to the n times 3 to the first power, right? And then in the numerator, I also have 3 to the n. And then down here, I have n to the third. So what I'm seeing is that the 3 to the n's cancel. And really, all I'm doing is taking the limit. This is 3 in the denominator. I'm going to bring that constant out of my limit. So that's going to be 1/3 the limit of n as n approaches infinity of n plus 1 to the third power over n cubed. Okay, so again, these are both to the same power. So if we wanted to, if this helps you, Sorry, I keep having to write this. Then I could write all of this as n plus 1 over n to the third power. Okay, sometimes that's helpful. Or you can also reduce this to be 1, see, since n over n is 1, and then plus 1 over n. Sometimes that's helpful when you're plugging in infinity, because then it's very easy to see that this part will be 0. And then I have 1 to the third. So it's going to be 1/3 times the limit of that will just be 1. So my limit is equal to 1/3. So what does that mean? Well, according to the ratio test, this ratio is less than 1. So that means this series is convergent. And it converges absolutely. Okay, so there we go. There's a ratio test. Let's do another one. Notice in this one we have some factorials. So again, this is a really good technique when you have factorials. So when you see that, when you see powers and factorials, think, okay, I got to do ratio test. So that would be the limit as n approaches infinity of, do your n plus 1 first. So that would be n plus 1 raised to the n plus 1 power over n plus 1 factorial. And we're going to multiply that by the reciprocal. N to the, oh, nope. That would be n factorial over n to the nth power. All right, so again, we can simplify this a little bit. So this would be the limit as n approaches infinity of, now if we simplify again the n plus 1 power, that's n plus 1 to the nth power times n plus 1 to the first power. And then again with my factorial, keep in mind that n plus 1 factorial is n plus 1 times n minus 1, okay, and so on. So that would be n plus 1 times n factorial. So that's the nice thing about factorials. So then what cancels is our n factorials and our n plus 1s. So I really have the limit as n approaches infinity of n plus 1 to the nth power over n to the nth power. And again, I like to, when I see that my power is the same in the numerator and denominator, it's helpful for me to write this as one fraction to that power. It helps me see. Now you might remember this. It's better if you remember this because the actual derivation of it is longer, but we can do that to help review. But this is actually equal to e. What helps me remember that is if I rewrite this like we did in the last one, the n over n is 1 plus 1 over n to the n power. This reminds me of the interest formula, and here the n is going to infinity, and remember if we compound continuously or basically infinitely many times per year, then that base of that power becomes e. So that helps me remember that. I think of interest. But let's review. It's always good to review logarithmic, taking the limit with logs. So here's how we do that if we forgot that, if we had to derive that. So we say y is going to be equal to the limit as n approaches infinity. I'm going to use this way of writing it. So what we're going to do is take the natural log of both sides. Remember this? I think we did this once. way back in first semester. And the reason we can do this is, remember, I can take a continuous function of a limit, and that's the same as taking the limit of that continuous function. All right, so I can say this is the limit as n approaches infinity of ln of all this stuff. And the reason we want natural log is so that we can bring that power in front, right? So we can bring that in front of my natural log. So that's always our technique. When we have a power raised to a power, or a variable raised to a variable power, we use that natural log, either in differentiation or with our limits. Okay, so what do we do with that now? Well, obviously, if I try to plug in infinity, I get a weird form of the indeterminate form. So we want to write it so that it looks like that indeterminate form that allows us to use L'Hopital's rule. So we use a little bit of creativity. I'm going to make this n, I'm going to divide by the 1 over n. Okay, so I'm going to rewrite this. I'm going to make this, instead of multiplying by n, I'm dividing by 1 over n. And then I'm going to keep this as the ln. And let's go ahead and, I guess I could have written it like I originally had it. 1 plus 1 over n. Because now when I plug in infinity, this becomes 0. And then if I plug infinity here, this is 0. So I'm taking the natural log of 1. The natural log of 1 is 0. So this is 0 over 0. That's our indeterminate form, which means we can use L'Hopital's rule. And so that means I can take the derivative of the numerator and the derivative of the denominator. So derivative of the denominator, remember, we're not doing quotient rule, right? We're doing the numerator and denominator separately. So the denominator is negative 1 over n squared. Remember, the derivative of a natural log is u prime over u. Okay, this is my u, and my u prime, it's the derivative of 1 plus 1 over n. Remember, derivative of 1 is 0, and then 1 over n is n squared. So that's my u prime. Over u, that's going to be 1 over 1 plus 1 over n. Okay, so basically the 1 over n, the negative 1 over n squareds cancel, and I'm taking the limit now of this guy. So why is that exciting? Well, this goes to 0, right? And then so I have that is equal to 1. Okay, so I have, don't forget all of this stuff, this left-hand side, this was natural log of y. So I have natural log of y is equal to this limit over here, which was equal to 1. And then if I solve this for y, I get e to the first power. Okay, so what does all that mean? Remember, I go back up here, this is how I got this answer of e. So in the midst of all this, remember, we're doing the ratio test, and the ratio test says that if this limit is less than 1, then it converges. So e, remember, is about 2.7, which is greater than 1, so that means this series diverges, since it's greater than 1. Okay, there you go. That's the ratio test. We'll be using that quite a bit. All right, so then let's look at the root test. The root test is very similar, except instead of ratios, we're doing roots. All right, so for the same reason, if I take the limit of the nth root of a sub n, and that is less than 1, then it converges. Right, notice that the criteria is the same as the ratio test. That's why these are kind of put together. And then it diverges if that nth root is greater than 1 or equal to infinity. And remember, it's inconclusive. All right, we can't use it if it's equal to 1. Okay, so that's the root test. Obviously, this is useful when we have powers of n. So that nth root is going to cancel with any powers of n. let's go ahead and look at example 4 on page 642. Go ahead and pause this video and get out your textbooks so you can see that and follow along. All right, so example 4. We are trying to determine the convergence of this series e to the 2n over n to the n. Okay, so big clue here. We have nth powers, so we're going to use the root test. So we're going to take the limit as n approaches infinity of the nth root of e to the 2n over n to the n. All right, so basically the n's are going to cancel, right? At least the powers in the n's. So this is going to be the limit of e squared over n. All right, so if I plug in infinity, this is going to be 0. So the e squared over 0, or infinity, which is 0. And 0 is less than 1, so that ratio, or it's not the ratio, the square root, or the nth root is less than 1, so that means it converges. Okay, so there's an example of the root test. Now, I do say look at the strategies for testing series on page 643. This is really nice. Now that we've learned all of the strategies we're going to learn in this unit for testing convergence and divergence, those guidelines kind of give you kind of like a procedure, things to look for, because it's overwhelming to have all of these strategies. So notice that they say, number 1, does the nth term approach 0? If not, the series diverges. So use that nth term test. That's a pretty easy test to do, and it works on anything, right? So if it's not equal to 0, then you automatically know it diverges. If it doesn't, then you know you need to go and search for another test. So the next thing is search for, is the series one of those special types? Is it geometric or p-series, telescoping, or alternating? So you've got those special types. So you have to be really good at recognizing, is it a geometric? Is it a p-series, telescoping, or alternating? Okay, so look for those. If it's none of those, then you can also check for, can you use the integral test? Remember the positive, decreasing conditions for the integral test. You've got the root test and the ratio test that we just learned, so those are the next things to try. And the last thing you should probably try are those comparison tests. Remember how we have direct comparison and limit comparison? Those tend to take a little bit more thought, so that's probably why they leave that at the end. But it kind of gives you a nice approach to all these problems. Okay, it gives you an organized way to look at your tests. Okay, and you should be getting a handout. If you flip the page, there's a summary for all those tests. You should be getting a handout with that on that, and kind of giving you instructions and some summary things to think about. So use that to help you study for that quest. You do not get to use that summary on your quest, so don't even ask. All right, but at least if you're studying it correctly, then you'll be good. And remember, for your quest, you need to be able to explain. If it's divergent, then why? Is it the nth root test? Is it this? So you have to be able to tell me why it's convergent or divergent. You can't just say, oh, because it looks like it, or I looked at a first few terms and that's why. Okay, so make sure you can justify your responses for series with one of those tests.